All right. So what I'm doing right now is to answer exam number 2 of CISP 440. This is a screen recording. I'm using Zerno so I can actually use my stylus to write on the exam itself. So this way it is resembling what you guys would need to do, generally speaking. So we'll start with getting the student ID, my last name, followed by my first name. And then we'll scroll down to read the instructions carefully. The exam time is from noon to 1:20 p.m. It is an individual exam. Paper-based content, can be used as long as it is prepared prior to the exam. Do not share, any of the content with other people. Grading is based on explanations and steps. Sufficient explanation means to answer the connect definitions and concepts. So this is where this is why I break the questions into multiple parts, because each part leads to this next part and so on. And so it's this part here, sufficient explanation, is sort of built into the answer the way it's formatted in this test. In no specific order, this is important. The properties of a relation are transitive, reflexive, comparable, antisymmetric, and symmetric. So these are not, intentionally, these are not the same order as they are introduced in the module, because I want you guys to figure out which one is which one. All right, so here's question number 1. You're given a relation R, and you're given R is defined over X, which only has 0, 1, 2 as elements in it. Within the scope of this question, we define function C0 as blah, blah, blah. And you can see it starts with the braces. It's enclosed in braces. So that means we are talking about a set. And the set only consists of elements, E, where E has to be an element of X, but ERE is false. In other words, we are looking for elements in X where it does not relate to itself in R. That's what C0 is trying to say. So that means if this particular set is empty, that means we cannot find anything in X such that it does not relate to itself, which also basically means everything relate to itself, which means if the cardinality of the set that is returned by C0Rx is 0, it means it's an empty set. This set is empty, which then means this is reflexive. There we go. All right, so moving on, I'm going to change my pencil just a little bit here because the thickness of my pencil is a little bit too thin. So hopefully this will not be too thick either. We'll see. All right, so the second one asks basically the same kind of question, but this time it is about C1. So we'll take a look at how C1 is defined. C1 of Rx is defined to be a set because we see the braces, where in this case, each element is a 3-tuple EFG. And I'm hoping that most people can recognize this part here comes from the property of transitive. So we are basically saying, if we can find E in X, F in X, G in X, such that, okay, because there's the and here, such that it is not the case that this implication is true, then EFG as a 3-tuple belongs to the set that we are creating on the fly here. In other words, we are asking, can we find EFG such that EF is related, FG are related, but EG are not related? That's what we're asking here. And if we cannot find anything like that, that means the relation over X is going to be transitive. There we go. All right. So these are the two answers to this question, and you will see that I recycled these definitions in the later questions. So we'll see these again. All right. So number 3 is asking me what is C0 applied to Rx. R is defined here. X is defined here. So that would be trying to find something that is not reflexive. In this case, 1 relates to 1, 2 relates to 2, but 0 does not relate to 0. So the proper answer is just a set with 0 as an element in it, and it is not supposed to be a tuple of 0, 0 because of the way this is formatted right here. We are only referring to the element in X that does not relate to itself. We're not looking for the two tuple in this case. So for C1, we are looking into R and we are asking, do we see any 3 elements in X such that together they basically indicate that the relation is not transitive. So since we already know that 0, 0 is missing, well, maybe that will help answer our question too, because we can make E 0, make F 2, make G 0, then 0 relates to 2 is true, 2 relates to 0 is also true, but 0 relating to 0 is false. So in this case, the element here is going to be 0, 2, 0. That is the 3 tuple that belongs in this particular set here. All right, so number 5 is asking if we let S as a set which is based on R, but we also add an extra element TU in it. T is an element of X, U is an element of X. We know that when we look at this new relation S, C0 of Sx is 0, which means it is reflexive. And we also know that C1 of Sx is also a 0, which means it is, oh, okay, so that doesn't work out. I'm mumbling here because my laptop is resting in a way that blocks the exhaust air from coming out. So the computer is heating up a little bit. But that's it's fixed now, so it's not an issue for us. Okay. All right, so now the question is, what element do we add to make it both reflexive and transitive? That is when, excuse me, the answers to number 2 and 3 and 4, parts 3 and part 4 comes in handy because we just have to add 0, 0 in it. The question is asking what is S minus R? So the answer is not, okay, repeat, it is not just the 2 tuple of 0, 0. It has to be the set that contains the element of 0, 0, like so. All right, so the next 3 questions are very similar. In question number 2, C0 is defined to be not RF, ERF, if and only if FRE. This part here is coming straight out of symmetry. So in other words, if there's a negation here, which basically means EF, both found in R, is going to make the relation not symmetric. So in the absence of that, because we're looking at the cardinality here, being 0. So in the absence of contradiction to symmetry, it is symmetric. So we say symmetric here. That's the name of the property. All right. The next one is this one here, which is the same thing that we saw earlier. So this one is just being transitive. Okay. So as you can see, once you start to answer the first question, the next ones would be a lot faster because the format is basically the same. And I even reuse some of these C0 and C1 definitions. So once you figure out the first one, the next one is going to be easier. Once you figure out like 2 of them, the third one is going to be a whole lot faster. All right, so next one is C0 of Rx. In other words, what evidence do we have that R is not symmetric over X? So we look at this and say, well, is it really not symmetric? And the answer is yes, because 0, 2 is here, but 2, 0 is not here. So that means ERF is not, okay, I shouldn't say that. It is not the case that ERF, if and only if FRE, when E equals to 0 and F equals to 2, but it can be the other way around too. So this is where it is important to know, what each element looks like in the set that is generated by C0. It is a set of sets. in this case, EF needs to be 0, 2 or 2, 0. So it would be a set where the element in it is just 0, 2. The reason why this has to be a set instead of a tuple is because if I make this a tuple, then you end up with 2 elements, because 0, 2 as a 2 tuple is part of the answer that meets this requirement. And then the other 2 tuple that meets the requirement of this answer is 0, 2 is one, 2, 0 is the other one. But if I make it a set, then there's only one single element here. All right, C1 is still looking at transitive. And in this case, I believe it is transitive already. So it would be an empty set here. All right, so for part number 5, I'm once again adding a new 2 tuple to the relation R, and we call the new relation RS. And we're asking, can we make this new relation symmetric, but it is not transitive, because this is transitive. So to make it symmetric, we need to add 2, 0 to it. By doing so, it is also going to be not transitive, because by adding 2, 0 to this particular relation, then it is not transitive, because 0, 2 is here, 2, 0 is here, but 0, 0 is not here. That makes it not transitive. So the correct answer to S minus R is going to be a set, and inside the set here is a 2 tuple, which consists of 2, 0 in this case. So that's the answer to question number 2. Moving on to question number 3, and we try to identify things that we have seen already. Yes, we do. Okay, so C0 is the same as the other 2 questions in this case. Now, whether you get the same kind of question, in this order is not guaranteed. I basically randomize how I combine the various properties. So in your case, it is possible that you do not get exactly the same ordering of the combination of the properties. But in this case, C1 is the same as the previous 2 questions, but C0 is not. So you can, when you look at this, it is the property of being comparable, or I should say it is the evidence of being not comparable, because we are looking for EF in X such that ERF or FRE is false, which means E and F are not related in any way, but it is still just comparable. There we go. All right, so number 3 is asking for evidence that this is not comparable. And in this case, you can also see how each element of C0 is supposed to be a set that has 2 elements in it. So now we say, okay, so can we find any evidence that the relation R is not comparable? And then we just say 1 relates to 1, 1 relates to 0, but 1 does not relate to 2. So we definitely have 1, 2 as a set here. And then we look at 2. 2 relates to 2. 2 relates to 0, but 2 does not relate to 1. But that's already covered by 1, 2. So we are not discovering anything new. And then we look at 0, right? 0 relates to 1, 0 relates to itself, 0 relates to 2, so 0, 2 is not going to be here. So this is the only element of C0. And then C1 is looking for evidence that this relation is not transitive. So we'll take a look here and see whether it is transitive or not. We see 1, 0, 0, 1, and 1, 1 is here, 0, 0 is here. It's good. We see that, let's see, 0, 1 is here. Okay. So I think, okay, let me go back to 2. All right, so 1 does not relate to 2 at all. 0, 2 is here. And 2 does not relate to 1. And all right. So we are looking for evidence that R is not transitive. All right. So we look at all the possible cases. 0, 1, 1, 0, 1, 0, 1 can only be related to 1, 1, and 0, 0. So we are clear there. And then we have 0, 2. And because 1, 2 are not related at all, that means in terms of transitive, we cannot really say anything that involves 0, 1, 2 in the 3 tuple because we are missing a link here. So now we look at 2, 2, 0, 2 is here, 2, 2 is here. We are missing 2, 0 to make it transitive of 0, 2, 2, 0, and then 2, 2. But that's okay because it's still being transitive here. So I believe it is an empty set here. So we make this an empty set. All right. So the next question is, what do we add to make it so that it is comparable and still be transitive? So for it to be comparable, we need we need 1, 2 as a 2 tuple or 2, 1 as a 2 tuple. So we'll figure out which one we should add. So we evaluate. Okay, if we add 1, 2 here, then everything is still good because if I add 1, 2, then we end up with 0, 1, and then we have 1, 2, and in terms of being transitive, 0, 2 is here already, so we are good. If we do it the other way around, which means we are doing it, adding 2, 1 here, it would also be okay because 0, 2 is here, 2, 1 will basically, if in terms of being transitive, will make it, we have to make sure that 0, 1 is here. So there are two possible options here. There's not a unique solution to this one. Oh, okay. So in this case, it is not going to be a curly because it is a 2 tuple. So you can use 1, 2 as the additional 2 tuple. It will make it work because this will fix the problem of 1 not relating to 2, but it doesn't cause a problem in terms of not being transitive because in this case we have 0, 1 and 1, 2, but 0, 2 is already here. So we are maintaining the relation being transitive, which is implied by C0 of Sx being 0. So we should be good there. All right, so moving on. So this one has two possible answers because you can also add the set. You can also union with a set of 2, 1. This will also fix the problem because now 2 is related to 1. And it doesn't cause a problem in terms of being transitive because we can combine 0, 2 with 2, 1, which means 0, 1 has to be in the relation and it's already in the relation. So we are good there. So you can probably guess that question number 4 is going to involve anti-symmetry because we have talked about all of the other properties already. So here's question number 4. The first one is symmetric. This one we have seen already in an earlier question. So this is just doing symmetric. And then the second one is the one that has to do with anti-symmetric. Anti-symmetry or anti-symmetric. Symmetric. There we go. Because we can identify this part here, okay, everything from here to here, that is the core of the universally quantified expression that makes a relation anti-symmetric. So we are basically saying, do we find any evidence that relation R is not anti-symmetric over X? So now we have to look for evidence of it not being symmetric. So it is not symmetric because 1, 2 is here, so 2, 2, 1 also needs to be here. So in this case, we have the tuple 2, 1 that needs to be here. I take it back. It should not be a 2 tuple. It should be a set. So we'll go ahead and turn this into a set, in which case the ordering of the elements is not important. All right, so that's one. The next one is asking, do we have any evidence that this is not anti-symmetric? The answer is no. We see no evidence that this is not anti-symmetric. So we put an empty set here. So the question, part 5 of the question is asking, can we just add one more 2 tuple to the entire thing so that it is symmetric, but it is no longer anti-symmetric because we find one counterexample to be anti-symmetric. So the answer in this case is going to be adding 2, 1 as a 2 tuple to R in order for the resulting S as a relation to be symmetric, because now 1, 2 has a matching 2, 1, but because of that, we also make the relation S not anti-symmetric, because now we can say right here, 1R2 is true and 2R1 is true, but it does not imply that 1 and 2 are the same, because 1 equals 2 is false. So now we have the left-hand side being true, the right-hand side being false. So the implication is false. So this would be the answer for number 4. All right, moving on to question number 5, which is exactly the same format as in the practice test or the test in fall 2022. All right, so to make this work, okay, we are going to have a bunch of disjunctions. So we'll go ahead and have not P or not Q or not R as one disjunction. We'll have this is not P or Q or not R. And then we have this one here, which is P or not Q or not R. In other words, we are basically just making a bunch of disjunctions where that disjunction is false only for a specific row. And by ANDing all of these things, we are basically putting all of these zeros in the truth table. So the fourth one is, okay, 1, 2, 3. The fourth one is over here. So we have P or Q or not R. And then the last one is here, which is just P or Q or R. And the question already tells you what we need to end up with, which is this one here. So that gives you a clue of what simplification we need to do. In other words, somehow we have to get rid of the not Q in here. And the way we're going to get rid of it is to combine the first two. So we'll say this is so I have to P or not Q or Q or not R by factoring these two. Now, after you factor, you can still put those things in the original thing. So so you can then just repeat the rest. Okay. The other way to do this, okay, let me see if I can, okay, let me erase all of this because I want to kind of emulate what you guys have to do on a piece of paper. And I have to make sure I don't erase more than what is in this question. Oh, okay, I'll just erase everything in this question here. I should still have enough time to finish the entire thing. So this one is not P or not Q or not R. This one is not P or Q or not R. This one here is P or not Q or not R. This one here is P or Q or not R. And then the last one is just P or Q or R. All right, so using factoring, we can use these two. And then using factoring, they become, when they're ANDed together, they become not P or not Q and Q, or not R, which is the same thing. And this, basically simplifies to 0, which then disappears. This is using factoring, which is the reverse of distribution. So the way we are doing this, the rule that we are using is, we recognize that we have A or B, and it is ANDed with A or C. And this is the same thing as A and, okay, let me think about this. Sometimes I forget about how to do all this stuff too. A and that's actually resolution too. I mean, if you look at this, that is actual resolution at work. So you can say this is done by resolution, but I'm going to try to do this using factoring. So I think it's the same thing as A and B. Oh, that won't work because one is a negation and the other one is not. So the only way to do it is to do it this way. Oh, wait, okay. Because P or not R is the common one. So we can factor that out. Okay, so let me go back. This is because I want to explain it using Boolean algebra. So it's still the same Boolean algebra that we're using, but I'm grouping the terms incorrectly. So we are still looking at a, let me it's out here. So we are still looking at A or B, and A or C is really the same thing as A and B or C. We're still looking at this here, except in this case, A is not P or not R, and the same applies here. The B is what we have not Q on one case, and then in the other one, we have Q not negated, which is over here. So by doing this, A is becoming just not P or not R, like so. B or C becomes not Q or Q, which then simplifies to a 1, which then simplifies out of existence because we have a conjunction and 1 is the identity of a conjunction. And that's how we end up with just not P or not R. All right, so the proper way to say this is it becomes not P or not R. That's one thing. And then we have not Q or Q as the other thing, which then simplifies to 1, which then simplifies to nothing. There we go. All right, so the next one is not Q or not R. So we have to identify two of these things that both have not Q or not R, and the one has not P, an extra not P, and the other one has the extra P not negated. So we can find these two. Okay, so we basically go like this one and this one. And then we say, okay, when we apply factoring, we have not P or not R left here. And then on the other side, we have not P or P. This simplifies to a true, and then the true simplifies to nothing when it is in a conjunction. And then the last one is looking for P or Q, and that would be these two combined. So these two combined would basically factor out P or Q as one term, and then not R or R is the other term. That simplifies to a true, and that simplifies away in a conjunction. So we end up with these three only. All right, so there is that. I also gave you in the announcement an alternative solution to solve all of this stuff here. It's a little bit more verbose. This is something I just thought of. Okay, so this is a little bit less verbose, but it's the same idea. We end up with exactly the same three disjunctions in the conjunction. We have not P or not R, We have not Q or not R, and then we also have P or Q left, as a result. And then we move on to the very last part. And this one is, somebody asked me about distribution. It really should not need distribution at all, because in this case, psi is a CNF already, which is actually from the previous question. And then phi is the negation of a CNF. But we have to remember that we are supposed to AND psi with the negation of phi. So that means, psi and not phi is now, basically not P or not R as one term, not Q or not R as one term, P or Q as one term. And then we have the negation of phi, and because phi is itself a negation of CNF, so when we negate that, we have double negation in front of a CNF, which means it's just the CNF itself. So now we just kind of copy not P or R, and then we have not Q or R over here. And in the announcement, I said, you can label these things 1, 2, 3, 3, 4, 5. So this way, it's easier for you to tell me how you do the resolution. And the idea is we want to get to false entirely, do just a 0. All right, so there are quite a few ways to do it. We can easily single out the R. Let me see. R is not that easy to single out, but we can single out not P easily by combining 1 and 4. Okay, so we have not P because we can use 1, 4 using R as the connector, because one has the negation of R, the other one has the non-negated R here. So the leftover is going to be not P on this one, and it's also going to be not P on this one. And then the next thing we want to do is to single out the Q, which is not easy. Okay, Q is not easily singled out, or is it? Well, we can easily single out the not Q, but Q non-negated can be, it can be singled out. Okay, fine, we're good here. So the idea to single out this Q here is to combine 3, and this is now 6, right? So by combining 3 and 6, we have Q left over. So we say this is number 7, which is the result of combining 3 and 6 using P. Then we end up with, okay, what was I doing again? Yes, so we single out Q in this case. All right, so if we can single out P, then we are done. If we can single out just Q, we are also done. Let's see. Yep, I did that correctly. And then the not P is also 1, 4. I'm just double checking to make sure that I did this correctly. All right, so if we can single out P by itself, it would be great. If we can single out not Q, it would be great too. Not Q can be singled out because of 2, 5. So now we say we can single out the not Q. And this is going to be expression 8 by combining 2, 5. And when we combine 2, 5, 2 and 5, we are using R as the connection. So now that we have these 3, we just have to look at 7, 8. Okay, so this is expression 9. By combining 7, 8 using Q, we get false. So because we get to false, we now know that phi is indeed a theorem of psi. So in your answer clearly shows how the disjunctions are resolved. So this method here is going to meet that requirement. In other words, for each application of resolution, you need to indicate which two disjunctions are utilized, and that's why we have these pairs stated here. And we'll go up a little bit to see what else I'm supposed to answer. Use the following area to show that phi is implied by psi using CNFs, resolution, and proof by contradiction only. You can use linear algebra only to prepare for the super CNF, which is the negation of phi, and that was super easy to do. You are explicitly allowed to apply absorption, but only when applicable. And in this case, it doesn't really help. It doesn't help to use absorption because once we single out the just the negation of a variable or a variable by itself, we can just use these for further resolution. We don't need to refer back to the earlier part. But to finish this entire thing, we can say because phi, psi and not phi implies false, then we say phi is a theorem of psi. That would be the conclusion. And that's it. This is the answer to the entire test for this particular version. So your version may be a little bit different, but the approach should be identical to what I just did here. All right, so I'm gonna push this on YouTube, and so this way you guys can take a look at it. All righty. So we will not talk about this in class unless there are specific questions about the solutions.